Okay, so we are on the ideal gas law, and we are moving into an equation that only uses one pressure, volume, quantity of gas, moles of gas, and temperature. So the simple gas law equations are concerned with the relationships between temperature, pressure, and volume, and they're really, really useful. And here what we're doing is we are simply keeping it to relating the amount of a substance or the moles of a substance to a pressure, a volume, a temperature, rather than changing them from one initial state to another. So P is pressure, V is volume, N is moles of gas, R is the ideal gas constant, which is defined depending upon the pressure units, and then T is the temperature in Kelvin. So if we take a look at the next page, we're going to talk about the ideal gas constant, and we learned that Avogadro's hypothesis said that a mole of any gas occupies the same volume as long as the temperature and pressure are being held constant. So here they're showing you helium, nitrogen, and carbon monoxide gas occupying the same volume, which is 22.4 liters, at a constant temperature and a constant pressure, and I have a mole of each occupying the same volume. So regardless of the identity, 22.4 liters of gas under standard temperature and pressure conditions, which is 273 Kelvin or 1 atmosphere, will always contain the same number of gas particles, which is 6.02 times 10 to the 23rd, or a mole. And that hypothesis allows us to determine the value of the ideal gas constant R by substituting a mole of gas at STP conditions into the ideal gas equation, PV equals nRT. So if we rearrange PV equals nRT for R, we're going to get 8.31 kilopascals times liters over moles times Kelvin. R has a fraction unit. If your pressure is in kilopascals, you want to use this 8.31 for the R value because you have to make sure that your pressure units are going to cancel. If we take a look at the next page at the quick check, here we're determining other values for the ideal gas constant R by substituting standard atmospheric pressures for P into the ideal gas equation. If you substitute 1 atm in, you're going to end up getting 0.0821 liters times atmospheres over moles times Kelvin for your R value. So if the pressure is in atmospheres, this is the R value that you would use. If you substitute in 760 millimeters of mercury to that equation, you're going to end up getting 62.4 millimeters of mercury times liters over moles times Kelvin. So if your pressure is in millimeters of mercury, you would use this R value. If your pressure is in PSI, then you would substitute that 14.7 in. You're going to get 1.21 PSI times liters over mole times Kelvin. So this is the R value that you would use. If you have kilopascals, you will end up with 8.31 as your R value, okay? Since all of those standard pressures were in 3 sig figs, the R values are all rounded to 3 significant figures. So these R values are what you're going to be referencing when you're using PV equals nRT. On the AP exam table of constants, they give you R values. They give them to you to a few more decimal places. You'll notice 8.314, 0.08206, 62.36. We're simply using the 8.31 for kilopascals, the 0.0821 if you're in atmospheres, and then the 62.4 if you are in torr. Let's go on here and talk about what an ideal gas is. Let me lower this down so that you don't have that glare in the board. Okay. The ideal gas equation should only be applied to ideal gases. What that means is gases that conform to the assumptions of the kinetic molecular theory. Two of the assumptions of this theory are, number one, molecules of a gas possess zero volume. So that means virtually all the volume of a gas sample is pretty much empty space. And number two, there are no attractive forces between gases. When gases collide, they collide elastically. That means the particles don't lose momentum following a collision. Now, if the pressure, let me talk about the temperature first. If the temperature is not too low and the pressure is not too high, most gases behave as if they are ideal, and that ideal gas equation is going to give you the correct answer, okay? So you need to keep in mind that the temperature should be high and the pressure should be low. That is when gases are going to behave ideally. So let's take a look at the next page, and let's go ahead and practice applying this concept. For the sample problem, we have a 1.45 liter container. So that's your volume with sulfur dioxide gas at a pressure of 115 kilopascals. That's your P. And your temperature of 28 degrees Celsius, that is your T. That has to be converted to Kelvin. If you add 273, you'll get 301 Kelvin for your temperature. Here they want to know how many moles are in the container. If you're using PV equals nRT, you need to divide by RT on both sides to get N equals PV over RT. You're going to substitute 115 kilopascals for P, 1.45 for V. Since your pressure is in units of kilopascals, you're going to use 8.31 for the R value. Your temperature is 301 Kelvin. Multiply and divide. You're going to end up getting 0.0667 moles. If you want to convert this to grams, multiply by the molar mass of SO2 to get 4.27 grams. Let's take a look at the practice problems. Find the volume of a gram of water if it were converted to the gas state at its boiling point at 100 degrees Celsius at standard atmospheric pressure. We need to convert this gram of water to moles of water. The molar mass of water is 18.02. That comes from 2 times 1.01 for hydrogen plus 16 for oxygen, which will give you 0.0555 moles of water. So that is your N. So if I'm looking for the volume, divide by P on both sides, you're going to get V equals nRT over P. Put 0.0555 in for N. Since we are at standard atmospheric pressure, and at standard atmospheric pressure, I'm going to use a pressure of 1 atm. Then I need to figure out what R value has atm in its unit, and that is 0.0821. And then I need to convert this 100 degrees Celsius to Kelvin, which is 373, and multiply and divide. You're going to end up with 1.70 liters. Now let's go to the next page. Let's take a look at practice problem number 2. At 30 degrees Celsius and 98.1 kilopascals, a 3.26 gram sample of an unknown gas has a volume of 3 liters. What is the molar mass of the gas? Assume it's a diatomic gas and identify it. The first step is determine the number of moles, then apply the unit grams per mole for molar mass to calculate the value. Okay, so anytime they ask you to calculate the molar mass of a gas, if we're using PV equals nRT, step number 1 would be to use the PV equals nRT equation to solve for moles, which is N. Then after you get that, in step number 2, you're going to take the grams that were given and you're going to divide it by N, which will be grams per mole, which is a unit for molar mass. So, my pressure was 98.1. My volume is 3 liters. If I look back at the R values for kPa, 8.31 kPa times liters over moles times Kelvin is what I'll use. Temperature needs to be converted to Kelvin by adding 273. You're going to end up with 303 Kelvin. You're going to get an N value of 0.117 moles. Now what you want to do is you want to go to step 2, take the grams that was given in the problem, 3.26 grams divided by 0.117 moles. That's going to be 20, I believe, I can barely read my writing, 27.9 grams per mole is the molar mass. Now, if I look at the diatomic gases on the periodic table, I'm looking for either H2, N2, O2, F2, Cl2. N2 is going to be the closest because nitrogen is 14.01. If you multiply that by 2, you're going to get 28.02 for its molar mass. So N2 is likely the diatomic gas that we're looking at here. For number 3, you can scan that with your phone, and you can do that yourself. Let's move on to derivations using PV equals nRT. Now, PV equals nRT can be used for a lot of different problems, and each of Boyle's and Charles and Gay-Lussac's, even the combined gas law, are kind of relatively easy to figure out. But there is a shortcut for the ratios to help us figure out what equation we should be using depending upon the situation. So let's take a look here at the quick check. For Charles's law, pressure in moles are constant. So if I include all of the variables in the equation P, V, N, and T, and I cancel out P and N because those are being held constant, the final form of the law is V1 over T1 equals V2 over T2. So that's Charles's law. Now, if I'm looking at Gay-Lussac's law, which has volume and moles of gas constant, if I cancel out those variables, so N is gone and V is gone, I get P1 over T1 equals P2 over T2, which is Gay-Lussac's law. For the combined gas law, I have moles being held constant. So if I cancel out N, I end up with P1 V1 over T1 equals P2 V2 over T2, which is the combined gas law. Okay? Now, there is another ideal gas law derivation. And if I have the ability to get the density of a gas, I can calculate the molar mass using this equation called the kitty cat equation, which is the molecular weight, or the molar mass, equals the density of a gas times R times T divided by P. Okay, the nickname comes from meow for molecular weight, and then dirt is what the kitty cats put on pee in their litter boxes. So that's where this kitty cat equation comes from. And if we're looking at the quick check here, it says solve problems 2 and 3 from the ideal gas law practice problems using the kitty cat equation. Compare your answers. Let's just take a look at practice problem number 2. For practice problem number 2, they gave us mass and volume, which means I can calculate density. So 3.26 grams divided by 3 liters is my density, okay? They told us that the pressure that we were operating at was 98.1 kilopascals. That's why my R value is 8.31. My temperature is 30 degrees Celsius plus 273 to get us into Kelvin. You end up with 27.9 grams per mole, which is the exact same molar mass that we calculated in practice problem number 2.